64-bit, I want to talk about how to turn off the 32-bit. What's going on here is actually more complicated than it appears, and I'll mention this. If you want to make your own, I put a link here so you can see how I made this, and it is kind of a mess. I made an Ubuntu server. You have to install a bunch of QEMU junk, a bunch of libvirt junk, a bunch of tools you have to install, download the Raspberry Pi and unzip it. Then you have to clone this Git repository that includes the kernels. And then you have to move it all somewhere and make it owned by root so root can run it. Then you have to run this thing called virsh to define the virtual network it's going to connect to. And then this makes it automatically start the virtual network every time you reboot the machine. And this is the command that actually launches the emulated machine, Raspberry Pi OS with architecture ARMv6L. This is the machine name. This specifies some of the hardware it's emulating. Here's this particular CPU it's emulating, which is the particular CPU appropriate for the Raspberry Pi, I think. I've just copied this from a bunch of blogs and pasted it together until it works. Then some memory and stuff. Then here's the disk, which is that image file that you unzipped, which already has Raspberry Pi installed on it. Then a bridge network, and no graphics. Took me a while to figure this out. At first I was getting a Raspberry Pi graphical screen, but that was like too big and clumsy. And then you boot this particular version of the kernel, and then you have to add this for the modern versions of this program. It requires you to give OS info, so you can give it a generic Linux answer. They don't know what Raspberry Pi is. Anyway, that's what all had to happen. So this was kind of complicated to set up, and you really have to have a clean boot to set up these networks. So if you just shut down the machine sloppily and restart it, it probably won't work. So the best thing is to shut everything down properly. And that's what so here I am in the Raspberry Pi. Let me see how many terminals I have. I have Raspberry Pi, and I have the Ubuntu, and here I have the console, which I'm not going to worry about the console. So in the Raspberry Pi, I'm going to do sudo power off. This will just turn it off in an orderly way. And you probably could just forcibly power it off from the virtual machine VMware, but I don't like doing that. I try to be kind to my machines to not corrupt them. So now I've turned off the Raspberry Pi, and I can verify that, by the way, with this command here. Not that one, but there is a command that lets you see what your machines are. We did it earlier, which is here. Not that one, but this one. This one will list all the virtual machines in QEMU on your machine. And so if I get rid of that one and run this one, I now give it a password. Now I see it's shut off. So the Raspberry Pi is shut off normally. And now I can do the same thing for the Ubuntu, sudo power off. Because I found before, if you suspend the Ubuntu and bring it back, it doesn't start those virtual networks reliably. So often when you get your Raspberry Pi running, you can't reach it. So it's better to just have it totally off and go through a full boot up when you want to use it. That's more reliable. All right. Anyway, so that's it for the 32-bit machine. Now, logically, I was just talking about, you could just use the Ubuntu here as your 64-bit machine, but I didn't think of that because earlier in the semester I made a Debian 64-bit to use for other projects, and so I wrote the project assuming you're using that. So anyway, I'm going to use the Debian. So there's a Debian I've had for months now. I just installed Debian 11 on ARM, and that's what Project 40 is. And the virtual CPU can be a higher frequency one if it exists. Yes, you're probably right, Ju. Yes. I haven't optimized any of this or tried variations. I just tried piecing things together until anything worked at all. That's as far as I got. But anyway, so now this is my Debian machine. I start a terminal and do IPA. And so I have an IP address here of 172.17. And so I just want to SSH into this one as before, because using the console directly is just really a drag. And using that graphical environment might be all right, but I've just gotten fed up with all that garbage and I like using SSH all the time. After you get used to it, it just seems cleaner. So 172.2017. And also, you can do all this with headless machines, but I did not know that at the earlier time. So this is a graphical Debian install, which is more than we need, but it's okay. So here I am getting in, and I say yes. and I give it a password. All right. Its password is Debian. Whoops. Okay, Debian, because I was imitating those precompiled Debian machines we're using for other projects. So now I'm in. Now I do uname -A, and I'll see I have ARM64 because I'm running on the Mac M1's hardware processor. This is not emulated. This is just a virtual machine running on my real processor, which is ARM64, which is 64-bit ARM. So let me just bring up my instructions and move them over to the other screen. This is now project 441. This one here, exploiting 64-bit ARM. So I'm going to move it over here, and you can do it on Intel or the Mac M1. Let's see, I'm just seeing, I saw a question mark there, but I don't know what that means. All right, anyway, so let me get to my instructions. All right, and back to my terminal. Okay, so we're going to have essentially the same vulnerable machine. Now, there was some hardware, there was some software I had to install here in the project, you'll see that, so you can compile on the ARM. It doesn't have that by default. And now I'm going to make a vulnerable program, which should be here if I do ls. Again, I called it pwd.c, and there it is. It is not quite the same. What happened is these exploits got kind of big, and I realized I hadn't left enough room to fit in here. I was getting weird crashes. They would work sometimes and fail sometimes, so I increased the size to 2,000 instead of 400 and 800, because it gets to be a lot of bytes. So that's the only change I made. I changed so that it can get up to 2,000 long and it'll read 2,000 characters. So other than that, it does the same thing. It copies it into a password field that only has room for 10, and that's the overflow. Now I'm looking here, the Alpine installation section has a displaying issue. Oh, okay. I don't know. We'll see. Good. Installation. Oh, my ARM on QEMU. Oh, thank you for telling me. Good. That ARM on QEMU is not something that most students are going to do. But yes, I just put that for people's information. Those are just sort of the notes I made while doing it, and I think there probably are some more mistakes in there. Anyway, so, all right. So now I'm in. I have the program, and so I can run that program, pwd, and I give it a password of AA. Okay. And if I give it another password of AA, then I've got address space layout randomization. This is F84, this is 620. So again, that's no fun. I do not plan to overcome that today. So I'm gonna fix that with the same old stuff. I just wanna copy this command here. Okay, sudo shu minus followed by this. So it's sudo shu minus to change to root, give it a password of Debian, and now go here. And now exit, and now it should stop that randomization. So if I give it AA, and then I give it AA again, I get the same thing. All F's 490, all F's 490. All right, these are not moving around anymore, which is what I want. And now I should be able to fuzz it. Now this 64-bit memory layout is different, of course, so it takes a longer input to make it crash. And we're gonna go through and see why this happens. So I put in a longer string, using only bytes ending in 4, and now I get the segmentation fault. So that's the fuzzing. I found a vulnerability, and now I can just go find the return address. So if I put it in a debugger, gdb -q pwd, and now I can I'm going to do the same thing I did before. I'm going to list 36 to 50. Okay, so here's the routine. And so I'm going to put a break here at 46 because the overflow happens there. So I break at 46. Now I'm going to run it. And I'm going to put in a short one of 10, 10, 10, 10. And examine the stack. I think 16 is probably, let's give it 20. X. Now, I'm not quite sure what the registers are called. I think they're still called the same thing. First, let's do info registers and see what the 64-bit registers look like. And they look like the 32-bit registers, which is very different than Intel, where it went from EIP to RIP. Here, they all look pretty much the same. There are more of them, though. And even SP and PC are still the same for stack pointer and program counter. So that's interesting. They didn't repeat the naming conventions of Intel. They just used pretty much the same names for the 64-bit registers, even though they're longer. So now I can examine the stack with, say, X20X stack pointer. Okay, and there we are. Now, one thing to note is 2 of these words are required for an address. So that's a 64-bit address, that's a 64-bit address, and so on. Here's the 1010s I put in. And now some of this might be return pointer. So to find out which part of it is, I'm going to disassemble the main. Now, when I do it, I can't read these stupid purple letters. So to get rid of that garbage, it's set syntax symbols. No, oh crap, I don't remember. It's set format. Style, that's it. Set style enabled off there. There, that gets rid of that. There. Now I can see this is the call to test PW, and this is the address it should go to afterwards. So it's going to be A's followed by 0C40. That's what the return address is going to look like. So let's look at the stack again and see if we can find that address 0C40. And it should be here, right there. And see, this is what I wanted to show you. Here is the return address. And here is the stuff I'm injecting. So this is what the student told me. They said, they read in a book that you can't do buffer overflows on 64-bit ARM because the return address is in a register. And that's not what I'm observing here, but it is similar. The return address is before the variables. So it has the same effect. I can overflow this as long as I want, and I'm never going to hit that address. So you might think I can't do a buffer overflow exploit, but that is not true. So let's try running it with the long input. And now I put in that same long input. Okay. And what happens is it hits the breakpoint. Okay. And now if I just continue, it crashes, and some of the data I put in ended up in the instruction pointer. So when I did this, I said, it's just the same. You overflow, you hit it. But what happened is, if you do it more carefully, you'll see why this happened. This is why I decided to write all these projects, because this was pretty fun. So if we run it again, we're going to do it another way. We're going to put in that long password, and I hit the breakpoint. Now I'm going to step through it. I think it's step to go to the next line of machine code. It's either step or next. Maybe it's next. Hold on, let me just Google that and get it right. I often get confused. GDB, step, next. What are these? Is it next? Okay, that's what continuing. Stepping means one more step of your program. Yeah, this is next. Next is what goes to one more line of source code, I think. That's what I'm looking for. F8 and F7, right? F7? F8 and F7. Right, it's also the difference between stepping into and stepping over, right? So step is there. Step steps over. And, well, I still want to know the difference between step and next. What is the difference between next and step? There we go. Step stops inside the called function. Next executes the called function, stopping on the next line. Okay, next is step over. Good. So next is what I want to just go through the source code. So now I'm here at line 46, and I do next, and I return successfully to the host program because I wasn't able to. Now, the other program would have crashed by now. I now returned from test PW into main. I'm in main. And I can see it. If I look at my source code by list, say 36 to 50, see, previously I would overflow it here, and when I went here, it would crash because it tried to return to main and it couldn't get there. But now it did return to main because I couldn't hit that return pointer. So, but if I keep going, now it prints all done. Let me print the source code again. I didn't get it all. Oops, 3655, there. So now I made it to this command and it executed it. But now if I do next, now it crashes. So I overflowed this variable and it crashed here. Because if you look at the stack, let me get back to that stack and you understand why this happened. It's actually pretty simple. If I run it, and now I put in a short thing, 1010, 1010, and now I examine the stack, say 50x stack pointer. Okay, Here is the return pointer for the test PW routine. Here's the variable I injected. Down here someplace is the return pointer for the main routine to take it back to the operating system, and then it's stack frame. So I overflowed right out of the stack frame of this one into the stack frame of the calling routine until I hit the return pointer for the calling routine to go back home to the operating system. So it's sort of crazy and stupid, but it does amount to the same thing. I managed to hit something and it ended up the instruction pointer. Now, I shouldn't be able to do this. And the only reason I was able to do this is I had to turn off yet another security feature to make this outrageous attack work. When we compiled this thing, I turned on yet another switch, making the vulnerable program. I compiled it with an executable stack, and I turned off the canary stack protector. That should have stopped this. I shouldn't have been able to overflow. So I turned off the stack protector. So I'm not entirely sure I'd overcome all these defenses, but I turned them all off. ASLR, stack execution, and the stack protector. If all that stuff is turned off, you can do this crazy thing of overflowing down to the next. So that's all. And then you can finish this attack, which is the same as before. Now that you've got control of the instruction pointer, you can make code with Metasploit. And when you do, Metasploit is even more limited. There were very few ARM32-bit Metasploit payloads, and there's even less ARM64 Metasploit payloads. That's all there are. There is no bind shell at all. The only thing there is a reverse shell. So you have to use that. I couldn't find any ARM stuff at all when I first did this a couple of years ago. So I couldn't find any Metasploit payloads at all. No, I found just a few. Anyway, so you can make that Metasploit shellcode. You have to include the address of your command and control server, which will be different if you're a Mac or if you're running on the emulated. And then you generate this code, make the finished exploit, and again, you'll have it'll phone back home and you can control your machine. I should be able to do that here. So if I get out of here and I look at the X3, there it is. So this, I've already, I think it's not going to work in this room. I think I made code that was tied to my network back home. Because now I don't have two layers of virtualization. I'm running a virtual Debian to my host. And in this room, the address is different, so this is not going to work. But anyway, I don't think I'll bother going through it. It's very much what we've done before.
Your Metasploit code is it tied to the IP address?
It is. When you make the Metasploit code, you have to specify the command and control address here. And so now if you're running on the Intel host, you had two layers of virtualization, and I know the addresses, they don't change because I defined them both. But here, the outside address is actually defined by the college. And so I'd have to regenerate the code. Anyway, that's what I wanted to show you. And like I say, all we've got is very simple exploits under very insecure conditions here. And I'm hoping to write some more projects where we can overcome some of these limitations, but I'm not sure I know how to overcome them all. I do know, looking at Azarea's stuff, Azarea is the queen of this stuff. Azarea is the expert of ARM exploitation. She just published a book. She has fantastic blogs and everything. And she knows how to do the ROP exploits, and I'm trying to get that far. So we can at least turn address-based layout randomization back on and get through that. These other defenses, I'm not sure we can punch through with any technique I know, but we can certainly do return-oriented programming to overcome the ASLR, and I'd like to have those projects in the next week or two. Anyway, that's what I wanted to show you. I'm going to stop the recording.